I want to do an example 4.43 from the Hibbler book, and I've got an image shown of it over here on the right. And I've stated the force in vector form and the position vector in vector form. So those should both be review at this point. We can calculate the moment, right, using the cross product of the position vector from A to C and the force vector at C. So that'll get us the moment vector about A. And here it is calculated. But it can be hard to visualize kind of how these all interplay. And so I'd like to walk through an Onshape example that gets the same values, but a little more graphically. So here I've got the same pipe shown, and I use the same dimensions as shown. And I've got a force added down here at the end of the pipe. Okay. So in this Onshape example, the force magnitude had been defined to be 80 newtons. Okay. The pipe was created. And then I've added a mate connector at point A and a mate connector at point C. If I actually select both of those points, I can use the measure details option and confirm the x coordinates. I need to fix my, this should be 550. This is always a good reason to confirm using Onshape. Right? So the pipe comes forward 550 millimeters, it goes to the right 400 millimeters, and it goes down 200 millimeters. Out here at point C, I added a mate connector, and it's been rotated relative to the end of the pipe. Might be easier to see from the top view, okay, how that's been rotated 40 degrees. And that's going to allow us to sketch the projection. That's going to take care of that 40-degree projection for us. Okay. So this force is sketched on that mate connector. And here is the 30 degrees below horizontal. And I've used my variable of the force magnitude, and I multiplied it by 2 millimeters. The 80 was pretty small relative to the millimeters, but I'm building everything off of the variable. Therefore, when I calculate my moment, it'll be off of the 80 rather than the length of this line. So this is a scaled representation on this sketch here of where that force is. And then with this force sketched at the end on point C, I create a plane, and this plane has both ends of the force, and it contains point A where the moment's being drawn around. So this is the plane that'll contain the position vector from A to C. So on this plane, let's show our force. There's our force. Okay. So here's the force at C. Technically, the position vector goes straight from A to C. This is my position vector. One way of calculating the magnitude of the moment would be R times F times the sine of the angle between them. So it'd be very easy here to add that angle on and get that piece of information if that was something we needed or wanted to use RF sine theta. Another way to use this sketch is I can take, and using the principle of transmissibility, I can take my force and I can translate it parallel over and draw the perpendicular distance from the moment to the force. So remember, this plane that we're looking at It's not horizontal, it's not vertical. It's a plane that contains the force vector and it contains the moment point. And in this plane, I can draw the perpendicular distance from the point to the force vector. And I can determine this perpendicular distance from point A to the force. And that's what we've done. We've drawn this sketch and we've gotten this perpendicular distance and created a variable based on what I call the radius about A, but the perpendicular distance to the force. Okay. So if I take the magnitude of my force, 80, and I multiply it by that perpendicular distance, we do get the moment. So the moment here has been calculated as 18,000 Newton millimeters or 18 Newton meters about point A. So that still doesn't quite explain kind of what does that mean? What does that value mean? How does this vector form get there? And just showing you that moment calculation here. We've got the force magnitude times that perpendicular distance, RA. All right. So to really picture what is happening, right, we've got our force, we've got our position vector, okay, both in vector form and as the perpendicular distance. The moment is going to be perpendicular to both the position vector and to the force vector. So we've, in this plane, which contains them both, we can actually create our sketch and extrude perpendicular to this. Let's turn off my mate connectors for a moment. Okay. All right. So here we've got the bent pipe. We've got the force applied down here at the end. And this green line is showing my moment axis. Now remember that moments are rotational. So this is the line that it would spin around. And it would have a length of 18 Newton meters if I were, I'm scaling lengths to rotation. But this is the axis it would spin around. So let's look at this kind of spinning around this pipe. If I look at it in the top view, right, my force is going to kind of spin, cause some rotation. Remember, this is my perpendicular distance to the force. So that force causes, I'm really not getting a lot from the top view, to be honest. Okay, let's look at, yeah, it's hard to, it really is challenging to quite grasp the 2D-ness happening here. But if I look at that perpendicular, that plane that I sketched, if I look at that plane, right, this is the force, that is the full force, I'm looking straight down on it, and this is the perpendicular distance, I don't see that moment at all. The moment is totally perpendicular to that plane. So when I look more at the side here of the rotation, right, or maybe more like this, right, so the force is tending to cause the rotation around this axis. Now, I offered to demonstrate how I can get these values on Onshape here. And again, we can use the measurement details. I'm just going to go to the end of the moment and come over here to this end of the moment and look at my measurement details. Right? And I can see that I have this. Actually, let's zoom this back out. Okay. So this moment has the -5. Now notice I'm off by a factor of 100. I've done some scaling to make it more visible or appropriate for the Onshape display, but I can confirm my X value, 5.39 in the negative X component. And then the Y value is positive 13.1 and the Z value is positive 11.4. So I could resolve this moment into those three components of a negative X component, positive Y component, and a positive Z component. And those values, while I have done some scaling, again, to make it fit the display model, does end up getting us the same values for the moment about A. So I hope that kind of helps us visualize the relationship between the force and the position vector and the perpendicular distance and the moment. Another way, maybe this is a great way to see it. Another way I've thought of visualizing the moment and why it's R cross F, I can kind of see it here. But if I think of R as the radius of a circle, and here's my force, and essentially there's a circle around here that force could be applied around, tending to twist around. Okay. That force times that radius would give us what I've demonstrated as the length of this moment. Okay. But the force, think of R as like a radius of a circle that we can spin around a point, causing rotation. I hope that helps.